The topic will be about folding a sheet of paper. Yes, 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 that very moment when we can't fold a standard office A4 sheet more than 7 times. I will not conduct this experiment directly for the camera right now. And actually, I don't have much paper here in this magnificent forest. But I will tell you that of course I try to do it, and of course the paper doesn't bend. And why doesn't it bend? Yes, in fact, simple mechanics are at work. Simple physics are at work. And here is the key to how it should be explained. You probably know that. The experiment, which was repeated by the Mythbusters using a huge sheet of paper, allowed the paper to be bent more than 7 times. That's also normal. And why was that the case? Let's figure it out. What actually happens when we bend a sheet of paper? What is bending? It is essentially two parts of the same material shift relative to each other. And what happens at the point of bending? This is a very important and useful moment for understanding, which should clarify everything that is happening. We have different... Oh, we will have to delve a little into complex introductory materials, but there's no way around it. We have a concept called mechanical stress. Stress can be tension, compression, and so on. We can easily see all this when we use some everyday objects. For example, when we stand on the ground, our soles experience compression. Accordingly, corresponding stresses arise in them. When we stretch an object, like an elastic spring or a door spring, tension occurs. And thus, the material always experiences several types of physical loading at once. Along with this, in order for the material not to break under, various types of deformation, we need the elasticity of the material to accommodate the loads we apply to it. This means that we cannot bend a glass plate in half, but we can easily bend a rubber plate of the same size. When the material is rubber, the outer part, at the point of bending, which moves, deforms freely. When it is glass, even the inner part cannot deform. Imagine a sheet of paper. It's not a sheet of paper at all, but a thick object with 2 walls. When the sheet of paper becomes as thick as a mattress for a bed, we find that the inner layer and the outer layer, this is chosen arbitrarily. Let's say the inner layer is on one side, to the right of this sheet, and the outer layer is on the other side. And we bend it inward to the right, this sheet of paper. And the sheet of paper is thick. Surface, inner layer. It just bends because it doesn't need to move, while the outer layer on the left needs to stretch to allow the connected part to move. Do you understand what I'm talking about? Here you can imagine perhaps a door on hinges that closes. And if you tape this door with double-sided elastic tape, you will see that where the door simply bends inward, opens inward, the elastic tape has folded. And where it needed to cover some distance, it either stretched or tore. The key circumstance for understanding this phenomenon is the appearance of additional distance. Now let's transfer this to a sheet of paper. As long as the sheet of paper is thin, the distance we see in the door, which tore the elastic tape, is minimal. Therefore, the paper's plasticity is sufficient for it to bend, without breaking. When the sheet begins to increase in size, initially some plasticity is provided by the fact that we have internal layers. They deform more actively, giving us some allowance for stretching on the outer layer, and the paper folds. But at some point, the number of sheets becomes such that we cannot bend this sheet without breaking it in half. In fact, it becomes equivalent to how we try to bend a sheet of plywood, which is also glued from many small wooden sheets. When we try to do this, we have 2 options. We cannot simply make the plywood bend. And the 2 options are either to break this sheet in half in order to fold it, or make such a radius, listen carefully right now, make such a large bending radius that the plywood bends without breaking. It will be roughly the same with paper. You cannot fold this paper when it is 7 sheets. But you can bend this paper. The difference here is that in one case we need to break the bonds between particles, between atoms of paper, and in the other case we just need to work within the framework of plastic deformation of this system. If we work within the framework of plastic deformation, then we can achieve much greater freedom. And the difference here is that when we have a small bending radius, when we have a critical radius, bending or allows only thin sheets of paper, only particles located at this point from this vertex, around which everything bends on the surface. Not far. We bend all of this. And when the radius increases, we have no choice but to tear the outer layer or, in fact, bend from an excessively large radius. And I initially mentioned that the Mythbusters had a huge sheet of paper that they were able to bend. And why were they able to bend it? What helped them do it? I think you already have an idea. The thing is, when the sheet of paper is large, our external and internal layers quite allow for it. These conditions are met. Our external layer gets a huge radius, at which there is no need to destroy the surface of the material, and the internal layer continues to bend freely. And the larger the sheet we have, the more times we can fold this paper. Fold. As you understand, there is a play of constant deformation and destruction. If the system is capable of deforming, it will deform. If the ability to deform reaches the limit of plasticity, then an option remains. Either tear it, or increase the radius to return to the limit of plasticity, again. You can help yourself a little in understanding. Take that very sheet of paper you are trying to bend, and the outer radius of this sheet, when you can no longer bend it, feel that a certain limit has been reached. Try, for example, wetting it with water. Wetting allows the particles to move more easily, increases the limit of plasticity, but when the material becomes too wet, it will completely fall apart. We are interested in that limit when the material has not yet completely disintegrated in water, but has gained some additional plasticity. And often, people write in the comments that they tried using a hydraulic press to fold it, but I couldn't do it, or on the contrary, I succeeded. Notice that the important thing here is not the fact that the paper folded, but the fact that there is such an interesting physical process related to the thickness of the paper sheet. And we are specifically interested in the mechanic's behavior. Of course, if you place an airplane, or something very heavy on it, you will probably fold the sheet. If you don't fold it, you'll just break it. But the discussion here is more about the interesting balance between forces that we have. And to reinforce your understanding, you can simplify the task for yourself. Take, for example, a blanket from an outdoor store. You've probably seen them, the shiny ones, the ones that are supposed to reflect heat back. This blanket, as far as I know, has the same thickness as a sheet of office paper. Now try cutting out a similar piece. From this blanket, that corresponds to an A4 sheet of paper. And try folding it as well, just like you wanted to fold the paper 7 times. When you start folding it, you'll realize that there is practically no limit to deformation. You will keep bending it, and at some point you'll realize that you folded it 16 times. I just picked that number out of thin air. I haven't actually tried doing it. But in any case, what's important here? That this material is significantly more pliable than paper. And with the same characteristics, with the same sheet thickness, we can successfully fold it a greater number of times. And why does this happen? Because pliability, let's say, is the key to understanding everything we've just discussed.